So, you've probably heard the term neural network thrown around a lot, but what's actually going on inside one? Like, what is it really? Well, that's exactly what we're going to break down today. We're going to pull back the curtain on the basic structure of a neural network, and we'll use a pretty classic example to help us out, teaching a computer to recognize handwritten numbers. Okay, so look at this. It's a pretty messy 3, right? It's not even high resolution. But your brain, it knew that was a 3 instantly. No problem at all. It's kind of amazing when you think about it, how we can just see it no matter how it's written. But now try to imagine writing a normal computer program to do that same thing. All of a sudden, this super easy task becomes a total nightmare. I mean, how would you even start? How do you write rules and code that cover every single way someone could possibly draw a 3? Every slant, every weird loop, every little stray mark? Yeah, that's the problem. And that's exactly the kind of challenge that neural networks were designed to tackle. So right there, that's the core of it. We have this huge gap between what's effortless for us humans and what's just brutally difficult for a computer. And that really sets the stage for why we need a whole new way of thinking. All right, so let's talk about that new way of thinking. Let's look at the actual blueprint of a neural network. We're going to break it down to its simplest, most fundamental parts. Okay, so the most basic building block of this whole thing is the neuron. And honestly, for what we're doing, it's super simple. Just think of a neuron as a little box that holds a single number. That's it. And that number has to be somewhere between 0 and 1. We call that number its activation. So if the activation is high, like close to 1, you can imagine that neuron is lit up or turned on. Now, these neurons aren't just floating around. They're organized into layers. For our little digit recognizing network, the very first layer is the input layer. Since our image is 28 by 28 pixels, that means we have 784 pixels in total. So our input layer has 784 neurons, one for each pixel. The activation of each neuron is just how bright that pixel is. Simple enough? Then you have the very last layer, the output layer. This one has 10 neurons, one for each possible digit, 0 through 9. Whichever one of these lights up the most, has the highest activation, that's the network's final answer. And all the stuff in the middle? Those are the hidden layers, and that's where all the real magic, the thinking, actually happens. Okay, so we've got the basic structure down. But why this way? What's the grand idea here? What are we hoping is actually going on inside those mysterious hidden layers? I mean, how does a machine possibly go from just a bunch of pixel brightness values to saying, yep, that's a 3? The whole idea, the hope, is that it builds up its understanding one layer at a time. See, the key is that we don't expect the network to just see the whole number right away. That's too big of a leap. The very first hidden layer, for example, might just learn to spot really simple things. We're talking about tiny little edges. So maybe one neuron in that layer is trained to light up only when it sees a little horizontal line, and another one activates only when it sees a tiny curve, and so on, for all the different parts of the image. And here's where it gets cool. The next layer doesn't look at the raw pixels anymore. It looks at the output from the first layer, the one that found all the little edges, and it learns to combine them into bigger patterns. So maybe one neuron in this layer learns that if a bunch of little curve-detecting neurons light up in a circle, it should activate. And boom, now you've got a neuron that recognizes a loop. Another neuron might learn to recognize a long straight line by seeing a bunch of smaller edge neurons activating in a row. And then, you guessed it, the final hidden layer takes those patterns, the loops and the lines, and puts them together. It learns that, hey, if the upper root neuron is firing and the long vertical line neuron is firing, then the number we're looking at is almost certainly a 9. And that's it. That's the beautiful idea of layered abstraction. You start simple and build up complexity. And this idea, this layered approach, is so powerful because it's not just for pictures. Think about audio. You could have a network that starts with raw sound waves. The first layer learns to identify simple phonetic sounds. The next layer combines those into syllables. The next combines those into full words, and on and on. It's the exact same principle, just with a different kind of data. Okay, so that's the big conceptual idea. But let's get down to the nitty-gritty. How does one single neuron actually decide whether to light up based on what the neurons in the layer before it are doing? Let's zoom in and look at the actual math. So every single connection between a neuron in one layer and a neuron in the next has a weight. The best way to think about these weights is like little volume knobs. A positive weight, high number, means that if the first neuron is lit up, it strongly encourages the next neuron to light up too. It's saying, hey, what I found is really important for you. A negative weight does the exact opposite. It says, nope, If I'm active, you should probably stay off. What I'm seeing is a bad sign. These weights are how a neuron learns what to pay attention to from the layer before it. So the neuron takes all the activations from the previous layer, multiplies them by their weights, and adds them all up. But there's one last little tweak. It adds another number, called a bias. The bias is basically just a measure of how easy it is for that neuron to fire. Think of it like a threshold. A neuron with a really high bias needs a ton of positive input before it'll even think about activating. It's kind of stubborn. A neuron with a low or negative bias is super eager to fire. It'll light up with just a little bit of encouragement. Okay, so we have this weighted sum plus the bias, but that final number could be anything, right? It could be 50 or negative 200. And that's a problem because we said a neuron's activation has to be between 0 and 1. So we do one last thing. We take that number and we run it through what some people affectionately call a squishification function. A common one is the sigmoid function. All it does is take any number, no matter how big or small, and squishes it down so it fits nicely in that 0 to 1 range. And that's it. That's the final activation. That's how a neuron thinks. All right, so that's one single neuron. Kind of simple, right? But what happens when you string thousands and thousands of these things together, all connected, all with their own weights and biases? Well, for the simple little network we've been talking about this whole time, there are around 13,000 of these parameters. 13,000! That's 13,000 individual weights and biases, all those little knobs and dials that we can tune. For a task that seems so simple to us, that is a staggering amount of complexity. And really, when you zoom all the way out and look at the big picture, that's all a neural network is. It's just one gigantic, ridiculously complicated function. It takes 784 numbers as an input, our pixels, and after all those thousands of little calculations with its 13,000 knobs and dials, it spits out 10 numbers as the output. It feels like magic, but at the end of the day, it's just math. A whole lot of it.
Which, of course, leads to the billion-dollar question, right? With 13,000 of these little knobs to tune, how in the world does a computer figure out the perfect settings to solve the problem? How does it know which way to turn each dial? Well, that process, that's what we call learning. And that, my friends, is where the real power of all this is truly unlocked.